Waves and sound. We're going to study how these things called waves really work in real life. And waves and sound are just an example of simple harmonic motion. So you looked at things like pendulums and oscillating springs, but simple harmonic motion is everything from light to sound waves to resonant waves to sonar to TV to music. Everything is simple harmonic motion. So everything is just a bunch of oscillations back and forth. So here we have a wave, and it's moving to the right. And let's picture the scene here. So let's suppose this is the ocean, and the waves are moving to the right. So you're watching the waves move to the right. And if you let time pass long enough, you would see that the tops of those waves would start moving to the right, and they would keep moving to the right. So if you watch it, it looks like the top is just moving to the right. And that's what we're going to be studying, so waves that are going to be moving. Now let's get some terminology down. Here is a certain distance, and this is defined as the amplitude. Now the amplitude is the maximum displacement away from equilibrium, where this dotted line in the middle is our equilibrium, and the very top of the wave would be the farthest it possibly goes from that, so that is the amplitude. And that distance is the same as that distance. So the amplitude is either up or down. So we have a positive amplitude right here at the top, and then we have a negative amplitude here at the bottom. And these things, the tops of the waves are called the crest, and the bottom of the wave is called the trough. So you can use these to make more easy measurements and get some calculations and be able to predict this motion more accurately. And the distance between the two crests is called the wavelength, and it's given by this weird symbol that looks like upside down Y. But this is called lambda, and I believe I spelled that wrong, but that's how you pronounce it, lambda. And this is the distance between the distance of one wave. So this is one wavelength. So that is called lambda. All right, let's look at a wave. Here's a wave, and it's moving to the right. And we're going to think about watching this one point right here. So as time goes on, the wave moves a little bit more to the right, and then it moves a little bit more to the right, and there, boom. We see that a crest passes that point every 2 seconds. So if it passes every 2 seconds, so one oscillation happens every 2 seconds, then that means our frequency is half a second. So we got one oscillation every 2 seconds. And then our period is 2 seconds. So our period is 2 seconds, and then our frequency is 0.5 hertz, so half a second, or half a hertz. This distance here between two tops of the waves to two peaks of the waves is 10 meters across, so 10 meters away. So if we know that distance, and we know how long it takes to cover that distance, then we can calculate a speed. So every time, if we look at one point, then in every 10 meters, we'll see a top of the wave every 2 seconds. So that means that wave is moving at 5 meters per second. So our equation for speed is just lambda over the period. Well, we can also say that since the period is the inverse of frequency, and frequency is the inverse of period, then the speed could also be calculated by lambda times the frequency, and we will get the same exact answer. We should get 5 meters per second. So 10 meters times 0.5 hertz, so that hertz is 1 over seconds. That gives us 5 meters per second. All right, here's another wave. We're going to do a couple of really basic calculations to get used to this idea of wave movement. And the frequency of this wave is 2.5 hertz, and the speed of that wave is 1.5 meters per second. So if you watch the top of the wave and you measured where it is over time, it's moving at 1.5 meters per second. So we can figure out its wavelength, and we can figure out its period. So its period is 0.4 seconds. So that means in 0.4 seconds, you should see the top of a wave pass the same point over and over. And then the speed of that wave is defined by frequency times lambda. So if we know its frequency or period and the speed of that wave, then we know that the tops of the waves are 0.6 meters apart. So if you look at the top of one wave, so if I look at, or let's say the bottom or the top, so the distance between here and here is 0.6 meters. Distance between here and here is also 0.6 meters. So our wavelength is 0.6 meters. Here's another one. So the period is half a second. The amplitude is 10 centimeters. Each wave is 0.4 meters apart. We could find its frequency and its speed. So its frequency is 2 hertz. So if the period is half a second, then that means we'll have 2 oscillations every second. So every second that passes, you can see 2 wavelengths that go by. And our speed is very easy to calculate. So our speed is just lambda times our frequency. And we're going 0.8 meters per second. So about 80 centimeters a second. Now let's look at a more unique property of waves. If you think of 2 cars that are about to collide, then it's pretty obvious what's going to happen. They're going to cause a huge mess, they're going to bounce apart, they're going to stick together, they're going to do something along those lines. Well, waves behave a little differently. So if I have a wave going to the right towards a wave that's going to the left, they're going to meet in the middle. But they're not going to bounce off each other. They're not going to collide. They're going to pass right through each other. So they're going to look a little weird. So you got, at one point, part of those waves are about to be in the same place. So their amplitudes are going to start adding together. And then it's eventually going to make a taller wave. If you've ever been to the beach and you see this weird occurrence where sometimes you have a wave going back out into the ocean at the same time a wave is coming towards the shore, you get this giant splash because those 2 waves are doing exactly what we're seeing here. They are going through each other and they are adding their amplitudes together. And then after that happens, then they keep going past and through each other like nothing ever happened, and they keep their original amplitude. Then what happens if one of them is a negative wave? So we've got a positive wave to the right and a negative wave to the left. Once they get to the middle, you can probably guess what's going to happen. One has a positive amplitude, one has a negative amplitude. Let's say it's 4 and negative 4. When they get to the middle, they're going to annihilate each other. So they're going to have no amplitude right here. So no, I'm going to just say A. So no amplitude. And if you're curious, this is actually how noise-canceling headphones work. So noise-canceling headphones, they measure the amplitude of the sound waves from outside, so the extra noise that you hear outside your headphones, and your headphones will produce a negative wave and play it at the same time. So that way, when all that outside noise gets to your ear and that negative outside noise gets to your ear, you don't hear anything. So that is how noise-canceling headphones work. Now, getting closer and closer to music and sound waves. But we need to look at these things called standing waves. And a standing wave is a wave that doesn't look like it's actually moving. It looks like it's just bouncing up and down. So if we have a string tied to a wall and we set it into motion, we can make it look like this, to where the left side is going to look like it's going down while the right side is going up. And then if you let time pass, then the left side's going to go back up and the right side's going to go back down. And it's just going to keep bouncing up and down. So the left side bounces up while the right side bounces down, and vice versa. And here we have a few new terms. This is called a node. So a node is where we have no amplitude, and the antinode is where we have the most. So the node looks like it's not moving at all, and the antinode looks like it's moving the most. Alright, so here's our wall again, and here's our string. And we're going to make this the longest wavelength possible. So if that side is a node and the wall is a node, then the longest wavelength possible would be looking like this. And it would bounce up and down. So we'd have one big wobble, essentially. So we'd have one wobble, and that would be half of the total wavelength. So that only is half of a sine wave. So that means the wavelength is 1/2. So this is called the first harmonic. And if you're in music, you probably know what I'm talking about. So this is the lowest tone, and we'll get to that in a second. Then what I can do is I could try to pinch the middle of that string and make that part a node as well. So then it could oscillate around all three of those nodes. So if I pinch the middle, then the left side will have a wobble and the right side will have a wobble. And then I'll have half a wavelength on the left, half a wavelength on the right, and this would be called the second harmonic. And we can keep doing this as many times as we want. So I'm going to try to get the next frequency or the next wavelength here where I've got 4 nodes. And then that would be half a wavelength, that would be half a wavelength, and that would be a half a wavelength. So we got 3 half wavelengths, then that would be our third harmonic. And we can keep doing this as many times as we want to. So our pattern that we saw was that the first harmonic, the length of the string was half the wavelength, then it was 2 half wavelengths, then it was 3 half wavelengths. So we can keep doing that forever, but you see the picture here, you see the pattern. So our wavelength is 2 times L over N, where N is 1, 2, 3, and so on. So multiply 2 times L over N, where N is each different harmonic, or each different wavelength that's possible. Then what would the frequency look like? So what frequencies could we get with this? Well, it would just be looking at our equation right here for the speed of a wave, and then substituting what we just now have. So we've got each frequency n that we could find would depend on each wavelength n that we could find. So it would look like this. So with that string, each n that we plug in would be a different frequency. So we get, if we used n over n as 1, then we get the first harmonic. N equals 2 to get the second harmonic, and then 3 we get the third harmonic. And if you think of any stringed instrument, this makes perfect sense because these would be different octaves of each other. So the frequency, any number frequency, is just that number times the first, where first is number 1 is the first harmonic. So that's the lowest frequency possible. Alright, now you probably see where this applies with sound waves. So sound, just like anything else we've been talking about, is just a wave. And sound waves visually, what they really are a little different than what we've been drawing. We've been drawing sine and cosine waves, where the things kind of travel up and then down and then up and down. But a sound wave is different, where a sound wave is more like an accordion. So we've got the air molecules in here getting compressed at these points, and they get stretched apart at other points. So at these points here, where there's lots of there's a lot of dots, that's where the air pressure is really, really high. And then in between that is where the air pressure is really, really low. So what we have is we have a longitudinal wave. So the wave actually goes like back and forth like this rather than up and down like this. Alright, but we can still use sine and cosine waves to visualize the math behind it. So that point right there is a compression, and then this point is called rarefaction. So high pressure and low pressure. So we can plot the pressure at the extreme points. So where there's the big dark blob, that's where we have a lot of pressure. And then we have, so this graph right here would be like pressure over time. So we have a high pressure here, low pressure there, high pressure here, low pressure here, high pressure, and then so on. So graphically, we could still think of this as more or less of a sine or a cosine wave. Now, here's what we'll be doing more in class. So we're going to be looking at tubes that are resonating with different frequencies. So we have a tube right here, and it's open at both ends. So that means we have an antinode at one end and an antinode at the other end. So we could figure out graphically or visually what kind of frequencies would come out of this. So if we have an antinode at one end and an antinode at the other, the smallest wavelength that would fit in here would be about half a wavelength. So it would look like this, where the length of that tube is half a wavelength for the lowest possible frequency. So middle part would be a node, and the ends would be antinodes. And just like our string that we tied to the wall, we could get multiple frequencies. So the next frequency is where we add another antinode, and we add another node. So there's still antinodes at the end, but now we added one in the middle. So then this would be the next frequency. So I'm going to substitute A's and N's here because I'm running out of space. So we've got antinodes at the end, the middle, and then we have nodes in between those points. And then that would be one whole wavelength. If you look, you have an entire cosine wave. It goes from the top to the bottom, back to the top. That's one entire oscillation. Then, so if we got tubes opened at both ends, it follows the same math that we had with our string. So each harmonic that we would get would just be n times half the wavelength, where L is the length of the tube and n is the next wavelength or frequency that we want. Alright, now let's look at what would happen if it's closed at one end and opened at the other. We would have a node at one end and an antinode at the other. So the lowest wavelength possible would actually be a quarter of the wavelength, because we go from the middle to the top amplitude and that's it. So if you look at this graphically, we are only going to here, which if we kept extending that wave, it would be this. So we only have a quarter of the wavelength. So this one's going to follow a slightly different pattern than what we did before. So that length is 1/4 of the wavelength. Length of that tube is 1/4. Now, keeping the node at one end and the antinode at the other, then our next wavelength would be 3/4 of a wave. So again, we look at our graph here. We go all the way to the top, through the middle, and then just to the bottom. Then the rest of that wavelength is only going to be a quarter. So we now have 3/4 of a wavelength. Then if we go to the next frequency, then it would look like this. So we can keep doing this over and over and over, but our frequencies aren't necessarily exact multiples of each other. So it follows a different pattern, where n is the wavelength, and then we have quarter wavelengths that keep happening. So then our frequency would look like this. It would be n times the speed over 4L. So then n is going to have to be odd numbers. So the first one was 1/4, the second one was 3/4, then it was 5/4, and so on. So it's going to follow odd numbers. Alright, now let's do an example with actual numbers. So let's say that our frequency that we found in that tube was 440 hertz, and I believe that should be middle C if you're a musician. And the speed of sound is 343 meters per second. And that speed of sound is what we are actually going to measure experimentally in class. So the question is, if we have that frequency, or if we want this frequency, and that's the speed of sound, how long should we make this tube? So if we're making an instrument, we could predict and measure how to build all these tubes to have different musical notes. So what would our length be, and then what would our next harmonic be? Let's answer that. So remember, our lowest frequency is going to be a quarter of the wavelength. So we're going to use our formula that we just kind of derived, and then we're going to solve that for the length. So we want the lowest frequency, so that means we're going to use n as 1, and then our frequency is 440. So then we just multiply everything out, and then the length of that tube should be 19.5 centimeters. So we could build a tube of 19.5 centimeters, and we would know that with the speed of sound, like if we made this into a flute or an organ pipe or something, that we would get the tone of 440 hertz. So what would the next harmonic be? What would the next note that could come out of this tube be? Well, this is following our open-close tube pattern, so the next number is an odd number. So we're going to use 3. And then calculate everything out, and then our frequency would be 1320. So that would be the next note that could come out of that tube. Alright, so when we get to class, we're going to start studying a little bit more sound waves, and you guys are actually going to make an instrument that I like to call a water trombone, where we're going to find the speed of sound using what we learned in this video.